Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So today we continue with chapter 3, which is the elements of transmission and distribution systems. But before that, we recite Surah Al-Fatihah. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Ar-Rahmanir-Rahim. إياك نعبد وإياك نستعين صراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين آمين يا رب العالمين. Okay, so this is the contents of chapter 3. So first one is the introduction more on the transmission system, and then cover with the transmission of electrical energy. Okay, and then the performance of transmission line in terms of the electrical system, and then design of transmission line, different systems of power transmission, comparison on volume of copper used for different power transmission systems, the classification of distribution system, design considerations in distribution systems, and finally the underground and overhead system. Okay, so we look on to the introduction. So introduction is the transmission system. So before this, I have covered with the complete system of the electrical system, which is starting from the generation, okay, until the distribution. Okay, so in this chapter, we will focus more on the transmission, the sub-transmission, and also part of the distribution systems. Okay. So first we will focus on the transmission system. So the transmission system is made up of the high voltage lines and bulk power substations that connect the generating stations, okay, with the distribution substations. So electrical power transmission lines can be HVAC, okay, HVDC, and then we have the underground or overhead lines. So basically for HVDC, this type of transmission system is used to transmit large amounts of power over long distances or for interconnections between asynchronous grids. Okay. And then long distances, because the HVDC used for long distances because more power loss if we use AC. Therefore, using HVDC will cut the cost. Okay. Meanwhile, for HVAC, this type of transmission system is used for the short distances. Okay. So overhead AC is the most used method of electrical power transmission, and then the transmission system can be divided into two lah. Okay, the first one is the transmission, and the second one is the sub-transmission. Okay. Okay, transmission of electrical energy. So high voltage transmission lines. So interconnect power plants and loads and form an electric network. So you can see here, when we connect all this, generation, transmission, sub-transmission and distributions, so it will form an electric network. Okay, so basically this transmission system contains 500 kV. Okay, we have for the transmission line, we have 500 kV in Malaysia. Okay, so 275 kV and also 132 kV. So the maximum length of the high voltage lines is around 200 miles, which equivalent to 320 kilometers. Okay. So the major components for this transmission lines, high voltage transmission lines are, so we can see here, this is we call tower. Okay, tower. Okay, tower is a lattice, normally steel tower, and then here we have, so this one we call tower, and then the second component is the insulator. So this one is the insulator. Okay, this is also the insulator. So insulator is a V-string hole, 4 bundle conductors in each phase. Okay, so this insulator will support the conductors and withstand both the normal operating voltage and surge due to switching and lightning. So this insulator is for the protection purposes. So basically it is made of wet processed porcelain or toughened glass. And the third one is the conductor. So you can see here, there is a conductor here, a bundle conductors. So each conductor is stranded steel reinforced aluminium cable. So you can see here, okay, this is the figure of the towers and also all the conductors. So conductors is basically the cables of the transmission lines. And this is the figure of the foundation of the transmission line, which is underneath the ground. Okay, next we look on to the sub-transmission. Okay, this one, sub-transmission. So this sub-transmission system is defined as the lines with voltage or capabilities between those used for transmissions, okay, this one, and also those for the distribution system. So in between of the transmission and distribution is the sub-transmission. So the purpose of these sub-transmission lines is to carry power from power substations, which is the generation, to the distribution substation and also to the large individual customers. The common voltage levels for these sub-transmission lines are 33 kV, okay, 33 kV and also 66 kV. Okay, transmission system in Malaysia. So transmission line in Malaysia mostly for HVAC transmission with a short portion HVDC to Thailand. So the transmission voltage at Malaysia are, we have HVAC 132 kV, HVAC 275 kV, and HVAC 500 kV. Okay. So next is the performance of transmission line. The transmission line performance is governed by its 4 parameters, which are, first is the series resistance R, okay, and then we have the series inductance L, shunt capacitance C, and shunt conductors is G. Okay, the equivalent circuit for this transmission line can be drawn as, so for example here we have R, L, and then we have G here, C, okay, so this is the equivalent circuit for the transmission line. So we have R resistance, we have the series inductance, we have the conductance, shunt conductors, and shunt capacitance. So the units for R is ohm, inductance is Henry, G conductance is Siemens or mho, and then C capacitance is farad. Okay, so the leakage current over the surface of the insulator is modeled as the shunt conductance G. So this one is the leakage current over the surface of the insulator. So usually shunt conductance is ignored because the leakage current is very small. Okay. So performance of transmission lines is meant the determination of the efficiency and also the regulation of lines. So in order to evaluate the performance of the transmission line, so we have to consider, first one is the transmission efficiency, the second one is the voltage regulation. So the transmission efficiency is, you can see the equation here, PR 3 phase, so PR 3 phase over PS 3 phase times 100%. So PR three-phase is the total real power. Okay, this one is the total real power at receiving end of line. At receiving end of line. End of line. Okay, and then we have PS three-phase. So PS three-phase is the total real power at sending end of line. So if you look at here, normally this one we have VS, PS. Okay, this one is voltage sending, power sending. And at the end here we have VR, voltage receiving, and PR, power receiving. So this part is the sending part, and this one is the receiving part. Okay. So to calculate the transmission efficiency, the equation will be the total real power of at receiving end of line PR three-phase divided by the PS three-phase, which is the total real power at sending end of line, times 100%. Okay, the second one is the voltage regulation. So voltage regulation is the percentage change in voltage at the receiving end of line in going from no load to full load. Okay, so the percentage of the voltage regulation is Vs, which is the voltage settings, minus with the VR receiving divided by the voltage receiving. Okay, times with 100%. So this one is the equation that we use to evaluate the performance of the transmission line, which are the transmission efficiency and also the voltage regulation. Okay, so next is the design of transmission line. So the design of a transmission line involve a number of technical and economic aspects. Okay, so normally the design details include, first is the line voltage. Okay, the voltage VL, and then we have the size of the conductors, and then the span, spacing, and configuration of the conductors, numbers and size of earth wires, and finally the insulators. So this is all the design details that we have to consider. Okay, we go one by one for the characteristic that we have to consider when design the transmission lines. Okay, first is the line voltage. Okay, so line voltage is the amount of voltage which a power line delivers to its destination. Okay, so the cost and performance of the line is depend on the line voltage. So this is an empirical formula for the optimum voltage. So we use V is the line voltage equivalent to 5.5 times L. L is the distance of the transmission line in kilometers over 1.6 plus P is the power in kilowatt over 100 to the power of 0.5. So second is the size of the conductors. So the cost of conductors is about 30 to 45% of the total cost of the line. The cost of tower, foundations, and line losses also depend on the conductor size. So bigger conductor size, of course, needs a bigger tower, foundations, and also high line losses. Okay, the size of the conductor should be able to carry the rated current continuously without excessive rise in temperature. Okay, and the temperature affects the set and the loss of the tensile strength of the conductor. Okay, so this is the figures of the conventional ACSR which is the aluminium conductor steel reinforced, and modern ACCC conductors. Okay, this ACCC is referring to the aluminium conductor composite core. Okay, so this is the types of the conductors that has been used for the transmission lines. Okay, and the third one is the span, spacing, and configuration of the conductors. Okay, so for high voltage line, the economical value of span lies in the range of 200 to 300 meters. But for 400 kilovolt lines, span ranging from 350 to 400 meters. Okay, so transmission line may be a single circuit line or a double circuit line. So a double circuit line has a higher power transfer capability and greater reliability. So this is the figures of the single circuit line. So you can see here on a single circuit line, and also there's a double circuit line. Okay. Okay, number 4 is the number and size of the earth wires. Okay. Okay, this is the figures of the towers, and also we have the conductors and also the earth wires. Okay, so selection of the earth or the ground wire. The primary function of these ground wires is to shield the conductors from the lightning strokes. Basically, it placed above the conductors. You can see here above the conductors. And grounded at every tower. So we'll have grounded here, every towers. Okay. The selection of the number and configuration is important in transmission line protection against lightning. Okay, so this is all the ground wire. And then a shielding angle of 30 degree is considered to be adequate for high voltage lines. So here, this one is the shielding angle or the protecting angle, which is 30 degree. Okay, and then a ground wires should be able to carry maximum expected lightning current without heating and have sufficient mechanical strength. That one is the purpose of the earth wire or shield wire. The purpose is more on the protection for the transmission system. Okay. Okay, next is the insulators. So the insulators basically is protection equipment that have been used for the transmission system. Okay, this is the figure of the insulators. So the insulation design has a greater impact on the performance of the line. Insulation should be sufficient to take care of switching, temporary overvoltage, and also lightning. So insulators are usually made of wet processed porcelain, okay, or toughened glass with increasing use of glass reinforced polymer insulators. Okay. So next, we go to section 3.5, different systems of power transmission. Okay. Okay, so for different systems of power transmission, so there are two types of power transmission, which are the DC systems and also the AC system. Okay, for the DC system, we have the DC 2-wire, DC 2-wire with midpoint earth, DC 3 wires. And then for the AC system, it divided to three sections, three types, which are, first is the single phase AC system, second is the two-phase AC system, and third is the three-phase AC system. For the single-phase AC system, we have single-phase 2-wire, single-phase 2-wire with midpoint earth, and single-phase 3-wire. While for the two-phase AC system, which is we have two-phase 4-wire and two-phase 3-wire. And for the three-phase AC system, which is the popular system that have been used, are the three-phase 3-wire and also three-phase 4 wires. Okay, from the previous possible systems of power transmission, It is difficult to say which is the best system unless and until some method of comparison is adopted. Now, the cost of material, the cost of the conductor material is one of the most important charges in the system. Obviously, the best system for transmission of power is that for which the volume of conductor material required is minimum. Okay. Therefore, the volume of conductor material required forms the basis of comparison between different systems. Okay, so this is example of the figure of DC2 wire. Okay, and then this one is a single phase 2 wire, with midpoint earth, and then two phase 3 wire and two phase 4 wire, and we have three phase 3 wire, three phase 4 wire. So this is all the various types of transmission systems. Okay, next 3.6, comparison on volume of copper used for different power transmission systems. So, in comparing the relative amounts of conductor material necessary for different systems of transmission, similar conditions will be assumed in each case. Okay, the first one is we have to assume that same power P watts transmitted by each system. The second one is the distance L meters over which power is transmitted remains the same. Third is the line loss W watts are the same in each case. And finally, the maximum voltage between any conductor and also earth, V maximum, is the same in each case. Okay, this is all for consideration, all for conditions that we have to assume. Okay, we look on to the first example, which is the overhead system for two-wire DC system with one conductor earth. Okay, right. When the transmission line is by overhead system, so the stress exists between the conductor and also earth. Therefore, comparison is based on the maximum voltage between the conductors. Okay, this one is the conductors and also the earth. So this one is V maximum. Okay, V maximum. So first, the maximum voltage between conductors is Vm. Okay, between the conductors and also the earth is Vm. And then power to be transmitted is P. So we will have the load current I1 is P over Vm. As we know that P equals to IVM, right? Okay. So if R1 is the resistance of each line conductor, then R1 equivalent to rho L over A1. Okay. So rho is the resistivity. So rho is the resistivity. Okay, resistivity of conductor material. Okay, and then we have L. So L is the length. L is the length of line in meters. Okay, in meters. And then A is the area of X section. Area of X section of the conductor. Okay, so line losses. So you have to calculate what is the line losses. So line losses is W, okay, equivalent to 2I1 squared R1. Okay, and then so you just substitute this one I1 here, so P over Vm squared, and then you substitute R1 here, okay, rho L over A1, okay. So the area of a X section A1 is, you formalize this equation, then you can get 2P squared rho L over WVM squared. Then you can get the volume of the conductor material required. So equivalent to 2A1L. So 2A is here. You just substitute in this equation. And then you will get this equation, okay, for the volume of conductor material. So say this volume is K. Okay. Okay, next is the three-phase, three-wire neutral point is Earth. Okay, so basically this one is the DC system, and next is the AC system. So this system is almost universally adopted for transmission of electric power. The three-phase, three-wire system may be star connected or delta connected. So here we can see in these figures is shows the three-phase, three-wire star connection system. Okay, and we can see here the neutral point and is Earth. Okay, the maximum phase voltage is Vm. Okay, you can see here, this one is the maximum voltage, Vm. Okay, so RMS voltage per phase is Vm per set2. So we got, then power per phase is P over 3. Then we have to calculate what is the load current per phase. So the load current per phase is, this one is I9. You can see here, this one is I9. I9 equivalent to P over 3, okay. You divide by Vm per set2 cos phi. So how you get this equation is from here, okay. So for star connection, we have to know that I line equivalent to I phase, okay, and then V line equivalent to set3 V phase. This is a basic knowledge of the three-phase system, okay, and then we know that P three-phase is set3 V line I line cos phi, okay, or we can also write the formula 3 V phase I phase cos phi, okay. So in this equation we use this formula. So we know that in this system the V phase is Vm over set2, okay, here. So this one is the V phase, okay. So you just substitute this one in this formula. So we know that P equivalents to 3 Vm, okay, Vm over set2 Ip cos phi, okay. Then what happened is, so Ip, so here we can write Ip is set2 P, okay, you divide by 3 Vm cos phi, okay, cos phi. So this represents this one, okay. And then after that, you have to find the line losses. So line losses and also the area of the X section. Okay, so line losses W by using this equation. So 3 because we have 3 numbers of conductors. Okay, then you just substitute all the equation I9 here and then R9, so you get this equation. Then you can get the area, which is 2p squared rho L over 3wvm squared cos squared phi. Okay, then you can get what is that one is the area. Then you can get what is the volume of the conductor material required for 3-phase 3-wire. So you just use this equation. Okay, 3 times 2a times L. So 3 because we have 3 conductors. Then you can get this equation. So from previous slide, I have informed that K equals equivalence to 4p squared rho L squared over WVM squared, right? So you just substitute here in this equation, then you can get the volume of this conductor material is 0.5 K over cos squared phi. Okay, next is the underground system. So when the transmission line is by underground system, the stress on the insulation is between the conductors. Okay, so here is the conductors. So the comparison based on maximum voltage is between the conductors. So this one is the V maximum. So the case here is two-wire DC system. So if Vm denotes the maximum potential difference between the conductors, so it will also be the working voltage in this case. Okay, so we look on the first one is we have to do the analysis same as the overhead system. Okay, so load current I1 equivalent to P over Vm. Okay, and then line losses W, so equivalent to 2I squared R1. So 2 because of we have 2 conductors. And then we can get the area of the X section E1. So this is the equation. Then finally we can get the volume of the conductor material required. So when we try to do all the substitute, all the formulation, we can get the volume of conductor material. P is equivalent to 4p squared rho L squared over WVM squared, which is K. So this K is similar as the overhead system, okay, as the previous slides that I have shown to all of you. So this value will be taken as the basic quantity and comparison shall be made for other system. Okay. So we look on to the underground system, 3-phase 3-wire AC system. Okay, suppose that the maximum value of voltage between the conductors is Vm. Okay, this one. So you can see here. This is the 3-phase 3-wire system. Then maximum voltage between each phase and neutral is Vm per set 3. Okay. Therefore, RMS value of voltage per phase is this one. Okay. This one is the RMS value for voltage per phase. Okay, this one. So RMS value for voltage per phase is Vm over set 3. You have to times with 1 over set 2. Then you get Vm over set 6. Okay. Then you get what is the power transmitted per phase is P over 3. Then you can get the load current per phase I9 is based on this equation. So same as the other overhead system. So you'll get the load current per phase is 6P over 3 Vm cos phi. Then you have to analyze for the line losses W. Okay, here is the line losses. Then you calculate for the area of section, this one. Okay, then you can get the volume of conductor material required is around 1.5 K over cos squared phi. Okay. So this is the table of the comparison on volume of copper. So this one is the system. You can see here all the system, the transmission system. We have DC 2 wire with one conductor earth, two DC 2 wire with midpoint earth, DC 3 wire, AC single phase 2 wire with one conductor, AC single phase 2 wire with midpoint earth, and also AC single phase 2 wire, 3 wires. Okay, so this is the formulation for the volume of copper required for the overhead and also underground system. Okay, so this is all the formulation. You can use this directly, the formulation directly, or you can derive lah from the first until you can get the equation for the volume of copper required. Right? Okay, this is also the continue from the previous slide, which is we also have the AC two-phase wire system, AC two-phase three wire, and also AC three-phase three wire. And also this is all the equation for the volume of copper required for overhead and underground system. Okay, we look on to the example 3.1. Okay, a 50 kilometers long underground transmission line supplies a load of 5 MVA. So this one is the apparent power. This one is the length of the transmission line at 0.8 power factor lagging at 33 kV. So the efficiency of transmission is 90%. So calculate the volume of aluminum conductor required for the line when first single phase 2 wire system is used, and the second one is 3-phase 3 wire system is used, which is the star connection. So the specific resistance of aluminum is 2.85 times 10 to the power of negative 8 ohms meter. Okay, this one is the rule. Okay. So the solution for the first example, so power transmitted is S times cos phi. So we know that S equivalent to VI, right? Okay. So and then we know that P equals to IV cos P. So IV is S cos P. Okay, so here is the equation. So S times cos phi, so is given the apparent power is 5 times 0.8, so you got 4 megawatt. Okay, and then or 4 times 10 to the power of 6 watt. So line loss 90% is the efficiency. Okay, the efficiency is 90%, so we can assume that 10% is the losses. So 10% of the power transmitted, so 10 over 100 times 4 times 10 to the power of 6. So you have 4 times 10 to the power of 5 watts. So length of the line is 50 kilometers. So 50 times 10 to the power of 3 meters. Okay. So you have to calculate what is the volume for the single phase 2 wire system. So the apparent power is S equivalent to V times I. Okay, so I equivalent to S over V. So S is 5 times 10 to the power of 6 divided by 33 times 10 to the power of 3. So you get the current is 151.5 amperes. Okay. So suppose A1 is the area of cross section of aluminum conductor. So so this line losses W is equivalent to 2I squared R1 equivalent to 2I squared times rho L over A. So area of section, you get equivalent to 2I squared rho L over W. So you get this answer. Okay, 1.635 times 10 to the power of negative 4 meters squared. Then you can calculate what is the volume. 2 times area with the length. Then you can get 16.35 meter cube. Okay, next is three-phase three-wire system. So line current I2 is equivalent to apparent power set 3 and then you have 2 times with the VL. Okay, V. So you know that equation for three-phase C as three-phase is equivalent to set 3 V line I line. Okay. So the apparent power, so we can get I, so I line equivalent to S over set 3 B line. So this one is this equation. So you get line current is 87.5 amperes. Then you have to calculate what is the area of section E2. So you have to calculate the line losses first. And after that, you can formulate using these line losses, you can get the area. So the area is 0.8111818 times 10 to the power of negative 4 meter square. Then you can calculate the volume of conductor required 3 times the area and also the length. So you get 12.27 meter cube. So note that the volume of conductor and hence weight requires less in case of three-phase three-wire system. So basically, normally three-phase three-wire system is adopted.